This is the first of 5 short films that explore molecular geometry. The first, part 1, is the lecture, and then the next 4 will be practice. By the end of the 5 films, you should be fairly well acquainted and be able to do most problems in order to predict the molecular geometry of a particle. What I want to show you next is how does the experiment we're going to do on molecular geometry fit into the overall bigger picture of bonding and what we've been learning so far in bonding. So I want to do a little bit of a review, very, very brief review, of what we've done, where we're going, and what we want to do in terms of the experiment. The position of this lesson in the bonding unit will be determined by what we've done so far. For instance, the first thing we do in the lesson is we talk about simple bonding definitions: covalent bonding, ionic bonding, the transfer of electrons, or the sharing of electrons. Ionic bonding is a transfer, covalent bonding is a sharing. But nothing is necessarily as it may seem. When we form a bond, we may partially transfer it or partially share it. This creates an imbalance in the electron cloud between two different elements. This almost transfer creates a kind of force, or we call it a polarity, between the two elements. We represent the bond using various models. We could be looking at a molecular orbital theory, or we could be looking at just everyday plain covalent bonding, and we could be using clay or gumdrops or ball and stick models in order to represent the molecules. Now remember, this is very static. When you write a chemical formula such as NaCl, that doesn't really tell you much about the behavior of NaCl. It doesn't tell you much about the bonding of NaCl. So we have other models that we will look at. With this particular unit, this bonding unit, we're going to be concentrating on covalent bonding, not ionic bonding. So when we have something, for instance, a common molecule such as carbon dioxide, we're going to look at how the elements are attached to each other. What is the central atom? What is the function of the central atom? What are the outer atoms? How many electrons does each element have to have? Remember, I don't like the name octet rule. I prefer to think of it as an element will seek to have a valence shell similar to that of a noble gas. So we have models. When we make these models, we're going to look at how the electrons are shared between the elements. And we look at the electronegativity. The electronegativity is the tendency for an element to attract bonded electrons. For instance, between carbon and oxygen. Oxygen is more electronegative than carbon, so there's going to be more of an attraction between the electrons towards oxygen. And that's going to create a polar bond because we have an asymmetric distribution of the electron cloud between the carbon and the oxygen. So we're going to be looking at all sorts of things when we do the actual gumdrop lab, I like to call it. You'll remember hybridization wasn't nearly as difficult as it appeared to be, but it's difficult to explain a particle that has a geometry of tetrahedral without understanding sp3 hybridization. It's difficult to understand how something can be trigonal planar for some things without understanding sp2 hybridization and linear for some particles with sp hybridization. Now, always remember that the double and triple bond represent one giant bond when you come to molecular geometry. It's one dipole, so to speak. You can think of it as one bond. Even though we know it's a double or a triple bond, we can still think of it as one bond. Even though with the valence shell electron pair repulsion theory, the double and triple bonds are considered one bond relative to the repulsion of other bonds, it's difficult to arrange the Lewis dot structure relative to geometry because there are only four sides of the symbol. So you do the best you can, you arrange them the best you can, and then when you actually make your model or predict the shape, you use other ideas in order to come up with your final geometry. So when you're predicting the shapes, you're using a combination of the Lewis dot diagrams and your understanding of the VSEPR theories. The molecular dipoles come from the fact that you have the polar bond and you have a dipole set up, and whether or not those dipoles literally cancel as in if they're vectors. So if one doesn't cancel, then you'll have a overall molecular dipole, literally as if you're adding vectors. And this creates an overall molecular polarity. So the only way a bond may not have polarity is if they are the same element, for instance, hydrogen bond, etc. But most bonds are polar because they're going to be different elements. And then even though you have a multiple number of bonds, it could be nonpolar. It's when those bonds don't cancel because of the geometry. So the properties of the substance that we're examining relative to the molecular geometry will in many, many ways be determined by the molecular geometry and the polarity. So the molecular geometry is going to be very, very important in order to come up with the properties of a substance. So let's do a problem, xenon difluoride. Now, even though xenon is a noble gas, because of its size, it can form compounds. So xenon difluoride. So the first thing you're going to come up with is going to be the total valence. The total valence. So you want to predict a shape. Well, xenon is going to be in the middle. So you're going to come up with a generalized shape of xenon difluoride. Just a way to come up with the central atom. And you're going to put xenon down, and you're going to put fluorine on either side of them. Now, this is not going to say that it's going to be a linear molecule. It may be angular or bent molecule, but you got to start somewhere. So you'll put xenon in the middle. So when it says determine the most likely arrangement of the atoms in the formula, it's going to simply be F, Z, Xe, F. So xenon in the middle and fluorine on either side. So you'll have two bonds one to each fluorine. So xenon will have 2 bonds, and each fluorine will have 1 bond. All right, so that's the approximate shape. Now, I'm not going to say at this point you don't have enough information to say that it's linear. You're just simply writing down something that's convenient, a convenient model given the facts. And the facts are simply this, that you have 3 elements, xenon's going to be in the middle, and fluorine will be on either side. So you want to count the total valence of the particle using a ball and stick model. Notice that ball and stick are in quotes, meaning that you're simply using a stick as a bond and a particle, such as fluorine or xenon, as the ball. Okay, so you want to count your valence. So xenon is in column 18 or 8A. Fluorine is in column 17. So they're going to have a valence of 8, 7, and 7. Will give you a total valence of 22. So there's going to be 22 total electrons that you can play with. So you either label the columns 17 and 18 or 7A and 8A. You can label them either way. One's more European, one's more American. I like to use 17 and 18. Just makes it a little bit easier. So there are, as you know, there are 18 columns in the periodic table, going from, say, sodium over to argon. All right, so here's the shape. We have 22 electrons that we're going to play with. Now, we want to subtract off. We want to keep a kind of an accounting procedure for each of the elements. So we know that we have 2 bonds. So it's going to be 2 bonds times 2, because there's 2 electrons in each bond. So that gives a total number of electrons as 4. So there are going to be 4 electrons total. So you're going to say total number of valence electrons is 22, and you're going to minus the bonded electrons of 4. Next, you want to complete the outer valence. Notice I say complete, because it already has 2 electrons, and you need 8, because it wants to be like the nearest noble gas. So each one is going to need 6 additional ones, because relative to the covalent bonding, it already has 2. So each one's going to be 6, so 2 times 6 is 12. So I'm going to subtract off an additional 12. You want to subtract the total number of electrons used to complete the valence. So now, I'm going to subtract 4 for bonding, and I'm going to subtract off 12 for completing the valence. So now I want to do some accounting, and I want to subtract 4 and 12 from 22, and I will get 6. So in other words, 22 minus 16 is 6. That gives me 3 pairs of electrons. So I have 3 non-bonded pairs of electrons. So what do I do with those 3 non-bonded pairs of electrons? What do I do with them? I want to put the remaining electrons around the central atom. Now, there's a rule relative to the central atom that you should be aware of. For a nonmetal, if the central atom is a nonmetal, let me repeat that. If the central atom is a nonmetal, you're going to, it says, if the central atom is a nonmetal, it must have at least 8 electrons. There are instances where the number of electrons around a nonmetal central atom is greater than 8 electrons. So, it must have at least 8 if it's a non-metal, and it can have greater than 8 electrons. So that's not going to be a problem. And that's going to be key in figuring out the geometry anyway. So you have 3 non-bonded pairs of electrons around the central atom. So now, as I put the electrons around the central atom, that's going to complete it. But now what I have to do is let me put them around so that it has some kind of arrangement. So, according to the Vesper rules, the 3 pairs of non-bonded electrons are going to repel each other. So if I have 3 around the central atom in a single plane, I know that they're going to have an angle of 120 degrees. They'll have an angle of 120 degrees. So I'm not sure I know that, but you're going to be able to, as you do these more and more, kind of be able to figure that out. And it's difficult to draw pairs of electrons on a piece of paper, two-dimensional, where it has a three-dimensional look, where I have the electrons around a central atom and it's 180 degrees, but you can kind of make it look that way a little bit with a little imagination. So there's my first 2 pairs, and then I need to put my 3rd pair around the central atom. And there's my 3rd pair. So it's difficult to illustrate, but let's just say that they're going to be 120 degrees from each other. So I have a note here. It says there are 5 sockets on the central atom. There's going to be 2 polar and 3 trigonal. The sockets which contain the non-bonded pair of electrons are the trigonal sockets, as opposed to the polar sockets, which have the fluorine. Repulsion indicates the bonded electrons will oppose each other in the polar sockets. So here are my parent shapes, and you're going to be able to see the one with the 5 sockets is going to be my trigonal bipyramidal. That's going to have 5 sockets. So that's going to be the parent molecule. And you can see that they're going to be, those trigonals are going to be in the middle that I have there. So you have 5 sockets, that's the parent geometry, and then you have 2 bonded pairs and 3 non-bonded pairs. So the parent geometry is going to be trigonal bipyramidal. That's going to be the parent geometry. Now, as we've seen before, it says put the remaining electrons around the central atom. So you have non-metal. If the central atom is a non-metal, it must have at least 8 electrons. There are instances where the number of electrons around the non-metal central atom are greater than 8 electrons. Now, to finish my thoughts, if it's a metal, in other words, the complete instructions would be, if the central atom is a metal, it may have less than 8 electrons. That may surprise you. But it can oftentimes have 4 electrons if it's a metal, or 6 electrons if it's a metal around the central atom. So they're a little bit unusual, but it can happen. Aluminum trichloride, for instance, is going to have 6 electrons around the central atom, just as an example. So you want to check with the shape grid to determine the shape. So we want to look now at the shape grid to see if we can figure out what the shape is going to be. So you look down on the far left, you look over to the left, it says total sockets. You look down and it says 5, so it's going to be on that line. So which one of those shapes, the parent shape is the first one, reading from left to right. The next one has one non-bonded pair. The next one has two non-bonded pairs. And the next one has three non-bonded pairs. And you can see quite clearly that it's going to be linear. So the shape of xenon difluoride, the shape of xenon difluoride is quite clearly going to be linear. And you can see it's the polar bonds that actually contain the fluorine, and the trigonal, it contains the non-bonded pairs. So you're going to look down, and it's going to be A. It's going to be linear. You have more than one type of linear molecule. So this is quite clearly going to be linear. Kind of a funny linear, but an interesting one nevertheless. So xenon difluoride is going to have a linear geometry. And I have a note here. Okay, there's the sign I put in green in the lower left, that it is linear. And it says, remember, the parent geometry is trigonal bipyramidal 5 sockets. It's going to be trigonal bipyramidal 5 sockets. That's the parent geometry. So now we want to draw in the dipole moments. We want to determine whether the particle has polarity or not. So first thing we do is we come up with the electronegativities. 1 decimal point is more than enough. So fluorine is 4 and xenon is 2.6. So based on the symmetry, determine the polarity. So we want to draw in the dipoles. Now, the dipoles are going to be going towards the fluorine because that's the more electronegative. So the direction of the dipole is towards the fluorine. And the dipoles are going to be the same. They're going to be equal and opposite. So you can see very clearly, based on the geometry, that the dipoles cancel. So if they cancel, you're going to have a nonpolar. So they cancel because you have symmetry. The symmetry, your bond symmetry is yes, absolutely. And the polarity is no, because they cancel. It's literally like vectors in physics. So now I want to review all of the shapes with you. Here are the shapes: linear, angular, trigonal planar, trigonal pyramidal, tetrahedral, square planar, seesaw, T, trigonal bipyramidal, and square-based bipyramidal. All right, so now with those, let's look at a little bit closer look at each of the geometries. So we have linear. We have several types of linear. We have two atom linear. At the end of each line is another atom. So we have linear, non-bonded pairs, 0, 1 bonded pair. We have 2 bonded pair linear with no non-bonded pairs. Okay, and then we have trigonal planar, and we have 3 bonded pairs, 0 non-bonded pairs. These are all the parent molecules at first that I'm doing. Instead of doing it per socket, I'm doing it per parent molecule. So we have tetrahedral, where we have 4 bonded pairs and 0 non-bonded pairs. And the next one, if you count up, you get 5. So 5 bonded pairs and 0 non-bonded pairs. That's trigonal bipyramidal. And octahedral. Octahedral has 6 bonded pairs and 0 non-bonded pairs. So you have 2 polar and then 4 in a plane. 4 in a plane. as opposed to 3 in the plane for the bipyramidal. Now we're going to get into the irregular geometry. So this is going to be bent or angular, where you have 2 bonded pairs and 1 non-bonded pair. So you have 3 sockets. So this is going to be related to the trigonal planar. That'll be the parent molecule for that. And you have there the non-bonded pairs and the bonded pairs. And then after this, you'll have trigonal pyramidal. These are 4 sockets, and these are all related to the tetrahedral. So you get trigonal pyramidal, and then you get a bent. It's like that second bent one, or angular, is like water. It's like water. And they're all in the, if you look at all 4 pairs, they're all in the tetrahedral shape. Now we'll take apart the trigonal bipyramidal. Now remember, these are all going to be the trigonal sockets. So if I remove one of the trigonal sockets, that's going to be a seesaw. So I'll have 4 bonded pairs and 1 non-bonded pairs. So if I take off just one, that's going to be a seesaw. Remember, not the polar, but the trigonal. Now, if I take off a second or a third one, if I take off 2 trigonals, that will leave me with the shape T. And if I take off a third one, that'll be similar or the same as what we just did, and that will give you linear. Now remember, don't worry if you can't represent it perfectly using a drawing, a 3-dimensional drawing. I'm not in the slightest bit artistic. Any artistic efforts that I show are completely either by accident or many hours of practice. I don't expect you to be able to draw these perfectly. However, let's go to the next with the 6 sockets. Now we have the 6 sockets. We have the square base pyramidal, where you have 1. Notice these are the polar bonds, the polar positions. You have the square base pyramidal, and then you have the square planar. Now remember, you are replacing the polar positions. And here they all are. This is your map of all of the geometries. Okay, study this carefully. I'm finished. Hope you had a good time, learned something. Have a good day, and goodbye.